Welcome everybody to Algebra 2, Section 7.6, Base E in Natural Logarithms. So let's talk about E and what it's used for and why it's used and all of that. So E, first of all, what is E? Okay, well, E is similar to pi. E is a number. It's not a variable. Pi isn't a variable. Pi is a number, and it's an irrational number. So let's fill in the blank here. It is an irrational number with an approximate value, and the approximate value of pi is 3.14159 dot dot dot. It just keeps going forever with no pattern or repeating. And E is similar. This number approximates, or starts out as 2. Oh, let me rewrite my 2. 2.71828 dot dot dot. And once again, with no repeating or pattern in there at all. So once again, that's 2.718, and I'm just fixing a couple of my numbers in there. And so pi, we know, is used for things such as with circles and spheres and cones and really lots of just different things that are round in nature, for finding area and surface area and volume and different things like that is oftentimes where pi comes in. Well, what's E for? Well, E is used for things such as exponential growth and exponential decay. And more specifically, continuous exponential growth and exponential decay. Continuous. So, for example, in 7.5, we talked about with interest in these word problems we had, where we had compound interest and we had intervals that it was compounded on. So we had intervals, and we said it was compounded quarterly or semi-annually, which was twice a year, or weekly, 52 times a year. And that was part of our formula where we inserted that number into the formula. Well, in this, theoretically, it's compounded infinitely often. And now, as far as calculating, we can't actually calculate infinity, and so E is what we use for this. And the E is actually referred to as Euler's number, and you might be like, well, Euler, that seems like it starts with an O, and Euler is a mathematician, and his name actually starts with an E, believe it or not. It's spelled, that's like this. Actually, I believe it's 2 L's there. Euler, and so it's Euler's number, is what it is. And he discovered this number and its uses for continuous exponential growth and decay. And many uses have been discovered since Euler's discovery of the number of E. There's a button on our calculator for E. There's other buttons on our calculator that utilize E as well that we'll be talking about today as well here today. So let's get into using E in various forms and whatnot today. And the ways we're going to be using E today are going to be very similar to the ways that we've been doing problems in this unit so far. So we're not going to do anything with E that we really haven't done with other things this unit. So natural base exponential functions. So we did exponential functions back in section 1, and now we're just going to do exponential functions with E as the base, as our B. So you remember we had B to the power of x, and so now we're going to have E to the power of x. And so, for example, the function f of x equals E to the power of x is exponential growth, whereas the function f of x equals E to the power of negative x is exponential decay. And so that negative turns it into decay versus growth. And this is continuous exponential growth versus continuous exponential decay, as I was talking about, that it is increasing or decreasing exponentially at every single second and every single moment in time, even fractions of a second that we can't even calculate, is the idea there. And so we're going to classify numbers 1 and 2 here as growth or decay. And then we're going to go ahead and graph them utilizing our calculator here to our advantage. And so on number one, we look at, okay, what number do we have in front of our x? Is it positive? Is it negative? Do we see a number there? We do see a number. That number is positive, and so thus this is growth. Okay. And then from there, I'm just going to go ahead and go to my graphing calculator. So I'm going to go to Calc 84 here. I have it pulled up over here. It might give me an advertisement. We'll see. That's okay if it does. Yep, sure enough. And I'm going to go to y equals. I'm going to clear out my function in there. And I need to type in e to the power of 0.5x. And so I'm going to hit my second button. And e to the power of x is actually this right next to the button 4. And it's the same on our TI-84s that we use in class. Right next to the our normal 4 button is a button that says ln. We'll get to that a little bit later in the lesson. And then above ln is e to the power of x. So I'll hit that. And I get e to the power of, and I'll type in 0.5, and I'll type in my x. And then I don't even necessarily need the graph right now, although that could be helpful to look at as well. But I need the table. So I'm going to hit second and go to graph to get to table. And so as I look at this table, I can look at some of these values. And specifically, I'm going to be looking at values such as, -2, -1, 0, 1, and 2. And we can see, oh, these are a bunch of messy decimals. And that's okay. We just are going to use some approximations here. And so as we use some approximations here, I'm just going to be rounding to, there's no exact science on number of decimal points that we really need. I'd be fine with any number of decimal points you want to use. So if you want to use 1 decimal point, that's fine. If you want to use 2 or 3 or 4 on these tables, that's fine by me as well. So on these, I might just use 2 decimal places here. On the test, I'll say kind of as a blanket statement for the whole test, hey, let's round to 4 decimal places. So maybe actually I'll round to 4 decimal places here just to kind of get us in that habit ahead of the test. So -2 through 2, so I'll have 0.2231. That is a 3 there, just kind of written poorly. -1 is 0.3679. I miswrote, I mislooked at my -2. I did -3's value. So -2 is the 0.3679. And -1 is 0.6065. Probably confused people there. And 0 is just 1. That's nice because that ends up being just e to the power of 0. And anything power of 0 is 1. And then 1 is 1.6487. And then 2 is 2.7183. Or 2.7183. I missed a 7 there. All right, and I'm going to just graph these approximately. It doesn't have to be perfect on my y values by any stretch of the imagination. That's for darn sure. I'm just looking for close on my graph, not necessarily perfect on my graph. And it might not be a bad idea to go a little bit out, maybe, especially as it climbs the graphs, like 3, 4.4817. That can be a good idea. Or maybe even if you wanted to, you could do 4, which not necessary. You could have stopped at 2 by all accounts. But 4 is 7.3891. It should be about there. And so I'm just going to connect this. And these still have these asymptotes, the horizontal asymptotes that we talked about at that y equals 0, unless we see that vertical shift translation slide of like a plus whatever. So this would have a +0 technically because you don't see a number there, but if it had a +1, then it'd be a horizontal asymptote at y equals 1, for example, like we talked about back in section 1. All right, open. I actually don't draw the arrows on the asymptote, but anyway. So that's what the number 1 graph would look like. And so then we'll transition to number 2. And so I would classify this one as decay, and the reason why is because it's negative there specifically. And so then I'll go ahead and make a table here. And I'll probably leave actually a little bit more room on the left side of my table specifically. And so as I go ahead and make this table, e to the power of negative 2x, go back to calculate 4, maybe it gives me another add. We'll see if I'm lucky. Maybe I won't be. Oh, maybe I'm lucky. And e to the power of delete, negative 2x. Don't necessarily need to look at the graph, although I could. It'll be decay, I'll know that. I can look at the x's, the y values, negative 2, 54. That's not fitting on the graph, but negative 1, comma, 7.389, or that, that can fit on the graph, And then all of a sudden they get really small, really fast. So it becomes quite unnecessary for me to do a lot of y values here because it gets, really small, really fast for those y values to where, doing a lot of these y values just becomes quite unnecessary. So I might just go from negative 1 to the to the x value of negative 1, x value of 0, x value of 1, and then I might just stop there, or even the x value of 2 at the latest, but I definitely don't need to go past that because these y values just get so small. So there's going to be such an insignificant change there. But anyway, so I'm going to do negative 1, 7.3891, because remember, at the end of the day, this graph is, this table is to help me graph it. That's the goal. And so I really just need to put in the table what's going to help me graph it. And so if I don't need to write down negative 2, 54, if that's not going to help me graph it, then it certainly will not help me graph it. So realistically, these are the only 3 values that I actually need to help me graph. So I could stop there if I really want, because this already gives me a pretty good idea what happens with this graph. So, and that'd be number 2. So let's move on to number 3 and 4 and do some applications, aka word problems. These were the same type of thing that we did in section 5 then, where now we just have e instead of different intervals of compounding perhaps, and so this is continuous compounding, so or continuous growth. So it could be in areas of finances with interest, or it could be with bacteria or population, or all sorts of different areas of uses with e and exponential functions in general. So a person is given 800 milligrams of a certain medicine. The amount of medicine in milligrams in their system after t hours is modeled by the function f of t equals 800 times e to the power of negative 0.6 t. How many milligrams of medicine remains in the system after 2 hours? So all it asks us to do is plug 2 into t and figure out what we get out. That's all we have to do here. So f of 2 equals 800 times e to the power of negative 0.6 times 2. So if we just type this into our calculator will do all of the heavy lifting for us. Now, could we, if we wanted to, actually multiply that out? Oh, I didn't mean to hit undo there. Could we actually multiply that out in the exponent and do negative 0.6 times 2 and call that negative 1.2? Sure. But, do we actually need to do that by hand instead of typing in our calculator? Well, no. Okay, so I'm just going to let my calculator do the work for me instead. And say, okay, well, this ends up being, approximately, I should say, 240.96. And once again, we could really round anywhere. There's, no hard and fast rule. So for the purpose of this lesson, I'm just going to round the 2 decimals. And once again, I could round to 4 like the test. I could round to 2. I could round to 3. I'm just going to say round to 2 right now for the purpose of this lesson. So 240.96 milligrams, because we always want labels here with word problems. At least I do, and I'm a stickler for them. So I'm going to make you do them as well. And if you're not sure what abbreviation to do, either one, look it up. We have the power of the internet. Wonderful time and age we live in. Or 2, just write out milligrams. Number 4, the balance in an investment account is modeled by the function f of t equals 2,000 times e to the power of 0.05t, where t is the years since the initial investment. Find the balance in the account after 15 years. That's a long time. Awesome. Okay. More longer it's invested, the more you're going to have out. So f of 15 in years equals 2,000 times e to the power of 0.05 times 15. And I'm just going to let my calculator do the heavy lifting here for me and say f of 15 is approximately, and we're going to definitely do 2 decimals for this one because money, 2 decimals is the pennies spot. So $4,000, $4,234.00 is what this approximates to. So you put this person put $2,000 in there. It just grew continuously, which is the best kind of growth. And for 15 years at a 5% interest rate, I see that it's 0.05, by the way. So I know how the formula works. It's that's the interest rate right there in this formula. And it over doubled in 15 years. How wonderful is that? That money just worked on its side. The person just got an extra $2,200 by just letting their money sit there for them. That's pretty cool. All right, let's move on to the next page here. So now let's talk about a natural logarithm. Well, just like any exponential problem, we learned back in section 2 that we can turn any exponential, back in section 3, that we can turn any exponential problem into a logarithm. And logarithms can just be helpful to solve problems in a different way, because logarithms and exponents are really the same thing. We learned that, for example, 2 to the power of 3 is 8. It can be rewritten as log base 2 of 8 equals 3. That those are the same exact thing. Okay, that what happens here is the 3 and 8 spiral or change sides. So the 3 came over to the right hand side and the 8 came over to the left hand side, and the 2, the base, stayed on the same side but changed size. It got smaller to go to logarithm, or bigger to go to the exponential side or the exponent on the left, and also changed position as far as the location of where it is. So it's either higher or lower, depending on which one it is, okay? So they spiral from one to the other. And remember, logs and exponents are really two sides of the same coin. They say the same thing, just in different ways. And the reason once when we do these, we have both of them. It's not just to make our lives harder, but actually to make our lives easier, because some problems are much easier to work with, and some things are much easier to work with when they are in terms of logarithms. And conversely, some things are much easier to work with when they are exponents. So we can also have a logarithm where the base is e instead of the base is 2 or whatever number we had. And when we do that, we call this the natural logarithm. Called the natural logarithm. And that's when it has base e. And so it can be written as, for example, log base e of x or whatever. But most often it's actually just written as ln x. Instead of log base e of x, you write as ln x. So it's like natural log, but ln, almost like it's log natural, just the reverse. And the one of the reasons we write it as ln rather than log base e on the right in orange rather than the left in purple is because it's less to write. And once again, it goes back to the theme of mathematicians are lazy. And so mathematicians just keep coming up with shorthands of ways to write things that are common for them to write. And so this became a common thing for mathematicians to write. And other fields as well, as I mentioned, use the base E for different things such as bacteria growth, finances, different things like that. And so they're like, hey, we're sick of writing log base E. And so we're like, hey, what if we just write it this instead? And so we write this instead now and call it natural log or natural logarithm, to say the long version. You'll just hear me say natural log, or ln is how it's often said. And so we say ln x, or natural log of x, or natural log of whatever. And so that's our shorthand. And so it's not wrong to write it on the left. It's not wrong to write it the way it is on the right. Similar to how if we have log base 10 of x, it's the same thing as log of x. If you don't see a base, it's secretly 10. If you have ln, the base is it's secretly log base e. They're the same thing. So in number 5, we're going to convert it from exponential to logarithm, and that's going to be 5, 6, 7, and then in 8, 9, 10, we're going to go the other way to go from logarithms to exponential. So in 5, e to the power of x equals 24, so we're going to do our spiral. So it's going to be log base e, which we're just going to call natural logarithm of 24 equals x. And that's our answer. Number 6, it's going to be spiral again. It's going to be log base e, which we just call natural log of x equals 9. On number 7, do our spiral again. It's going to be log base e, which we just call natural log of 72 equals x plus 5. Now on number 8, we're going to go the other way. So we spiral. Natural log was log base e. It's going to be e to the power of 58 equals x. Number 9, spiral. I see our base is secretly e because it's natural log, which means log base e. So e to the power of x equals 6. 10, spiral. Everything that's in the parentheses is what it's there for, telling us the whole thing's part of the natural log. Natural log means log base e. So it's going to be e to the power of 32 equals x minus 9. Now, we can condense and expand natural logs the same exact way we condense and expand any logarithms. So we treat base e the same way we treat any other base, whether it's 2 or 4 or 12 or 10 or whatever. So even though we write it differently, ln, we treat it the same way. It's just a shorthand way of writing it is all. So we're going to condense it. And so a reminder from our properties that we learned that addition is not really addition when it comes to logarithms. It's actually multiplication of the insides. So it's natural log of 3 and 16. Well, we multiply those. It's 48. On number 12, when we see subtraction, it's not really subtraction, it's actually division. But also, when we see coefficient, it's not actually coefficient, it's actually exponents. And so this is actually 3 squared. And so this becomes natural log of 63 over 3 squared. And so I have to do 3 squared and then divide 63 by that result. Because order of operation dictates I do the exponent first. And so this becomes natural log of 63 over 9, and that becomes natural log of 7. 13, they both have coefficients, and then I will add them, or aka multiply. And so I get natural log of 64 to the power of 1/3. Well, that's really the cube root of 64. And if you're unsure of that or don't remember, your calculator can always assist you. Raise 64 to the power of 1/3 in your calculator, and your calculator will tell you, hey, that's 4. Plus natural log of x squared, or, and then you multiply those together, and you just get natural log of 4x squared. Can't do any more there. If you type that in your calculator, 4 times x squared, your calculator will give you a number, but it's not actually that number. Your calculator just gives you a random value for x. So I would recommend that. So now on 14, 15, 16, we're going to expand it. So remember, multiplication is not multiplication. It's really addition here. So natural log of 5 plus natural log of x. Fully expanded. Number 15, before we expand, let's make those exponents into singular exponents. So natural log of a to the power of 6 over b to the power of 2. Now we can expand these into 2 separate logarithms, each with a coefficient. 6 times natural log of a minus, because they're dividing, 2 times natural log of b. Wouldn't be the worst idea to put a little tail on your L's here, by the way. That way you can tell apart natural log from ones. Just an FYI. On number 16, this is a cube root. Remember that cube root is a power of 1/3. So this becomes natural log of m to the power of 2/3, n to the power of 1/3, because it's numerator over denominator. And this has a secret numerator of 1. And so this becomes 2/3 times the natural log of m plus, because they're multiplying, 1/3 times the natural log of n. So sometimes putting a little multiplication dot between the two can help, or you can utilize parentheses there as well. You put multiplication dots, the little bullets, they can be called as well, can be quite helpful as well. Lots of things can be helpful to clarify. Well, now let's start solving equations. And just like before, we can solve equations with logarithms, and we can solve them with natural logarithms. And we also have to check for extraneous solutions. And our parameters are the exact same as before, where we cannot have the log of a negative. And we have a 1 log on each side, and so we check to see if we can condense them. We can't, and so they're already condensed. And so we just drop the logs and set the insides equal. 4x minus 27 equals 15 minus 2x. And now we start solving what's here. So I'm going to move my x's together by adding 2x to each side and get 6x minus 27 equals 15. Add 27 to each side and get 6x equals 42. Divide both sides by 6, and I get x equals 7. And before I box that, I do check, hey, if I plug in 7 to both of these logarithms, do I get the log of a negative? And either one produces a negative, so we're fine. On 18, I have a log on each side again. However, I can't condense this one, so I need to. A coefficient is really an exponent, so I have natural log of k squared. Equals natural log of 2k plus 15. So now I can drop the logs, and so I have k squared equals 2k plus 15. And now since we have an exponent of 2, we want to move everything toward that exponent of 2 and then seek to factor. So I'll have k squared minus 2k plus 15 equals 0. And once again, factoring is going to be my fastest way to solve this, typically. And we can factor, so I'm going to do, that should be a minus 15, because I would have to subtract it. And so it's going to be a times c, so 1 times negative 15, and b is at the bottom is negative 2. And it's going to be negative 5, positive 3 to do the trick. And I can do my shortcut here since it's 1k squared. So I'm going to do k minus 5, k plus 3 equals 0. I can set each one of them equal to 0. And then add 5 to each side to get k equals 5 and k minus 3, or k equals negative 3. And then I check for extraneous solutions, and as I check, 5 works in both, so 5 is fine. But negative 3 doesn't work specifically in this left one. And so that one is extraneous. And so we label it as such. Moving on to number 19 here. Logs on both sides, and this time both sides need condensed. So on the left here, we subtract, which really means that we're dividing. And so we get 72 divided by 4, which is really 18. On the right side, we add, which really means we multiply. So 6 times a and 2, which gives natural log of 6a minus 12. And now we can set the insides equal to each other, so we get 18 equals 6a minus 12. And so that gives me, as I add 12 to both sides, 30 equals 6a. And then divide both sides by 6. A equals 5. And I can't plug 5 into any of these that are just numbers, but if I plug 5 into here, it works just fine and doesn't produce a negative. On number 20 here, I do need to condense this 2 here. It's an exponent. And so I have natural log of m plus 4 quantity squared equals natural log of 4. I can't just distribute this 2 here since there's either an addition or multiplication inside the parentheses, in this case addition. So I actually need to do m plus 4 and write it out twice and actually work on foiling and combine like terms. And as I FOIL, I get m squared plus 4m plus 4m plus 16, which just combines to be m squared plus 8m plus 16. So it's natural log of all of that equals natural log of 4. And so now I can drop the natural logs and do m squared plus 8m plus 16 equals 4. And so now since I have an exponent of 2, I set everything equal to 0 and move it toward that exponent of 2. And so I'm going to have m squared plus 8m plus 12 as I subtract 4 equals 0. And if I go ahead and make the x here, and I do 12 at the top, 12 times 1, and 8 at the bottom, and I have positive 6, positive 2 to do the trick. And I check, can I do my shortcut? And sure enough, I thankfully can do my shortcut here since it's the 1m squared. I can do m plus 6, m plus 2 equals 0. And so I can do m plus 6 equals 0, m plus 2 equals 0. And then as I solve, I get m equals negative 6, m equals negative 2. And as I plug these in to check on them, I notice negative 2 works just fine here. Can't plug it in the other one. But negative 6 doesn't. It produces a negative. And so that one is going to be extraneous. So now as we move on to number 21 here, I'm going to notice, hey, I don't have logs on both sides anymore. I only have a log on one side. And we encountered the same thing in section 4 when we were solving logarithmic equations, just normal logarithmic, not natural logarithmic. And these we handle the exact same way, where we still isolate and condense a logarithm, or the one side with logarithms, and then we spiral it and convert it to exponents. And so this side is condensed and isolated, and so we'll spiral it, convert it to exponents. And so what's being raised to power is e when it's natural log, and so it's e to the power of 2 equals 8x. And so now to solve this, we utilized our calculator and said, okay, whatever was raised to a power, type in our calculator, then figure out what that was. And so e to the power of 2, according to our calculator, is 7.3891, approximately speaking. And that's approximately 8x. And so we divide both sides by 8. In our calculator, we just hit divide by 8. And that tells us x is approximately, to 4 decimal places what I'm doing here, 0.9236. And we can just call that good. Let our calculator do the heavy lifting. And that's using the same e to the power of x button as we used when we did exponential graphing earlier in the lesson, which was the second natural log button next to the 4. So number 22 here, same setup where we have natural logs on one side, but numbers on the other. And so we condense this here. So we have subtraction, which is really division. So natural log of x over n equals 7. And so this is going to be a spiral where we have the base is e, so e to the power 7 equals x over 9. And so e to the power 7 is, according to calculator, approximately 1096.6332. And so then as we multiply both sides by 9 to get rid of the 9, x is approximately 9,869.6984. Now, number 23, we have another type of problem, and we encountered this same type of problem before as well, where we had exponential problems that we did not have common bases, and we can't get common bases. We can't turn 57 into e to the power something, or at least not well, and we'd be there here all day trying to figure out what it would be to be exactly 57 and not just approximately or close to. Um, and that'd be quite the pain to try and do that. So no, thank you. So here's what we do instead. Actually, there would be no exact; it would only be approximate, I should say, because since e's are rational. But what we do anyway, and it's the same thing we did back in section 4, and that's isolate what's being raised to a power, and then convert it to a logarithm, and then utilize our calculator as well. And so this becomes log base e, or natural log of 57 equals x. And then this is where we utilize, instead of second natural log, we just use the natural log button on our calculator and type in natural log of 57 and hit enter. And our calculator says, hey, that's actually approximately 4.0431. And we're done. So on number 24, we do the same thing, but this time we have to get e to the power y plus 3 by itself before we can convert it to a logarithm. We have to add 6 to both sides. E to the power y plus 3 equals 30. Now we convert to a natural log, or a logarithm that has base e. And so natural log of 30 equals y plus 3. And so our calculator tells us, hey, natural log of 30 is approximately 3.4012. And so if I subtract 3 from both sides, I end up getting y to be approximately 0.4012. And once again, this is the same exact way we solved problems before, when we had the variable and the exponent of one side, and we couldn't get common bases on both sides. So just drop the bases. On number 25 here, e is being raised to power, but 5 is not. So we need to get rid of the 5 by dividing it to undo the multiplication. And e to the power of 4n equals 19. And now we spiral. And now we get natural log of 19 equals 4n. And our calculator tells us natural log of 19 is approximately 2.9444. And so then we divide both sides by 4. And that is approximately 0.7361. On the number 26, here e once again is what raised to power, so we get rid of the 2 and the 3. We get rid of the 3 first because we're doing reverse order by undoing things. So we're doing SAD map, not PEMDAS. So we have 2e to the power of c minus 9 equals 84. Then we divide both sides by 2, and we get e to the power of c minus 9 equals 42. Now we convert it to a logarithm, and we get natural log base e, of 42 equals c minus 9. Natural log of 42, or ln 42, according to our calculator, is approximately 3.7377. And so, if we add 9 to that, we end up getting 12.7377 to be approximately c. And that wraps up section 7.6 of Algebra 2. And we can see here that, as we learned about e and natural logs, that all things we did with e today are just the same exact things we did throughout the rest of the unit with other bases that were raised to powers or of natural logarithms, which are the same thing as exponents, just written differently. And we just applied them to e today as well. And did all the same things as we did before. We just wrote them a little bit differently because we wrote e with them. So maybe we wrote natural log, and we called it continuous growth and continuous decay. And really, that's all that was different, was how we wrote it. But any of the math we did was really the same. We just pushed a couple different buttons on our calculator. Instead of doing log, we did ln. Instead of doing 7 to the power of something, we did e to the power of something. With that, we close out Unit 7 of Algebra 2.